First of all, thanks for coming. And I would like also to thank the organizer for having included also our diagnostic division here to share with you all our information. So in the next 15-20 minutes, I have the hard task of summarizing our sample processing. And because I do know that this is not the most charming part of the entire conference, I have the hard task of keeping you awake. So let's start with that. So the genetic testing process is not as easy as it seems here. So basically, we are not like CSI or NCIS, where they generate the report in a blink of an eye. Although we have to say that there are technologies nowadays that allows you to get the report in a very short amount of time. But if you are dealing with a ultra-rare complex disease, such as atypical aHUS, what you have to think is that you should keep in mind that it's not how fast or soon you get your result, but how is it interpreted. Because you see from the previous speeches that the genetic cause of atypical aHUS are still an open chapter. And also, moreover, only one single simple test for this disease does not exist so far. If you see here, this is what happened in our lab. So we have functional tests, we have genetic tests, and I will go through the genetic test today. And they are combined in a workflow like that. The final report is basically is the result of different tests, not only one. And moreover, and this is the most important and exciting part, is that the final report is coming through from a different process. We have, it is generated when the clinician, the diagnostician, and the clinical team gather together to discuss all the results we obtain from each patient every week in what we call the renal meeting. This is great, to my personally speaking, I mean. And this process means also that we are not a factory. So for us, each sample has a name, has a story. It's not just like we are handling each sample as just an ID number. But if I wanted to explain what we exactly do, so what is a molecular genetic testing? So let me show you here. So once we got the DNA, once we extract the DNA from your blood, from the blood of a patient, we focus our attention on some specific region of the DNA. They are called genes. Each gene is made up by different building blocks that are called introns and exons. Only the exons then are transcribed first, translated later into the final protein. And this is due to the presence of cell machineries in our body, our cells. So what we do is basically analyze with different techniques all the exons sequences in order to find out if there are any abnormalities that could lead to a defect protein, like in this case. So going back to this workflow, I go through these three main different techniques we are using right now in our lab. The MLPA, which is the MLPA, the Sanger sequencing method, and the latest one, the newest one, I would say, the next generation sequencing. when I talk about Sanger sequencing, this is the most common test performed in every genetic lab. But I would like to show you this. So until last year, we were sequencing manually, I underline manually, 7 genes involved in atypical aHUS. And I said before that what we are studying exactly are the exons. So we have 119 total exons that we have to screen manually. What does it mean that? The process, I won't go through each single step because it will take a lot of time to me to explain, but what is important here is that this process is a multi-step process, so you have to work hard to get the result at the end. So, and you have to consider also that this process is repeated for each single exons. And once you think that you get the product and you put in the machine, you get the result, you are not very close to the end because there is a lot of work to do, again, more. So this is the result we got. It's called a sequencer trace or electropherogram. It's basically represent here are peaks or bases of the sequence of the exon. Alteration to DNA are basically detected by comparing the normal DNA sequence, like this one, to the patient DNA sequence in this way. You can think, okay, it's finished. No, it's not. What happened? So basically, you put this in a program. There is a software that can determine or flag each difference from one to one. Don't look this one. It was my mistake. Sorry. But so there is a software that can do that, but it's not sufficient. So we have to go through all the 119 exons, and better, we have to go through each single base that form these 119 exons, which translate in numbers. We have to screen visually, by visual inspection, 50,000 base pairs. So it means that we have to look for 50,000 times these peaks. There's a lot of tons of work. And honestly, what can I say? If you were looking before from an eventual difference between the two sequences of the DNA of a patient, I can show you this is a kind of what we are looking for exactly. So it's also tricky sometimes. So it's not very clear, and you have to be very careful when you do this kind of reading. One thing that I have to apologize, because until last year, our turnaround time for give a result to the people, I was 6 months approximately. But now you can understand that it was, somehow, I would say somehow justified. somehow. But fortunately, from this year, we start to have this kind of new technique. So we translate this technique, which is called next generation sequencing, into patient care. What is generation sequencing? This term, NGS, is often referred to a massive parallel sequencing, which means, in few words, that millions of small fragments of DNA can be sequenced, like before, in a very short amount of time and all together. And I would like, first of all, to thank, and I'm really grateful to our researcher that developed what we call this thrombotic microangiopathy panel. So it's a panel of 10 genes that it's not useful for atypical aHUS. It's also useful for other TMA disorders. As you can see here, and also, sorry, I have to thank also the foundation for having purchased some important instrumentation that are required for doing this kind of analysis. Most important here is, as you can see, the difference between the previous electropherogram and the result that we got now. It's fantastic. It's way easy to ingest. this kind of report is made by informaticians who did a very great job on doing that. So it's more easy and understandable for us. As you can see, the table, this report is broken in two tables. The upper table is where we reported the possible variants that are disease-associated or disease-causing atypical aHUS. In the lower part, I reported all the other variants that are common. We call polymorphism. So common in the, you see the frequency of these particular variants that are present also in the healthy population. But when we look at this, we don't look only for the genetic cause of the disease. We also have to look the quality of the data we got, because this is the other side when you perform a genetic test. We have to see how is the quality of the data we got, because it could be a false positive. We have to figure out if it is a false positive. So we look this data, and also here, you see it's not easy to say, okay, I found a mutation in a patient, the patient carried this mutation, it's finished. No, we have the possibility to verify using basically internal quality control system that allows us to be precise in what we are doing. So in this case, when we identify a positive patient, what we do is going back, re-extract the DNA of the patient, perform a Sanger analysis like the method I showed before to just look for that specific variant in that specific exon. So we are sure that what the new technology does is correct. And then we discuss this at the renal meeting. The last method we are using is called Multiplex Ligation-dependent probe amplification, MLPA for friends. It's a very useful technique for detecting large deletion or duplication, and specifically also for rearrangement, genetic rearrangement that could happen between the factor H and the related genes of factor H. So it's complement related 1 through 5. The last two slides are what are the good side of the making a screen, a genetic test, and the dark side of the genetic testing. So you listened before, Dr. Nestor, she was saying exactly the same sentence here, basically the same idea. So when we do a genetic screening, the positive thing is that you could have a good prognostic information. So you have a mutation, you know what to do, what kind of mutation is, and how can affect the patient. You can have a better correlation between the genotype and the phenotype, so the clinical feature associated with the kind of specific mutation you have. And then it's also important for the suitability for possible transplantation. It could be isolated renal, it could be liver, kidney transplantation, but also it can tell you if there is a possibility of what kind of recurrence rate for atypical aHUS after transplantation. So it gives you precious information. And then the last one, and I think it's really important, is that the unaffected carriers could be better monitoring during triggering events. For example, a woman who carried the mutation during the pregnancy could be better monitored by the doctor, because we all know that pregnancy is one of the biggest triggers of atypical aHUS. But unfortunately, this is the dark side of the diagnosis or the genetic testing. First of all, when you probably know or are familiar with this term, the variant of unknown significance, what does it mean? This drives me nuts every time we find a mutation that we can say if it is disease-causing or if it is associated. So we have some tools we call in silico software predictor that can help us to figure out if the variant we identified is somehow disease-associated or disease-causing. But most of the time we are not, we don't have this possibility to say this is definitely disease-causing. So because the only way perhaps to say to have the definitive result is coming from functional assay. But functional assay are too costly and time-consuming for a normal genetic screening. So it's not feasible, unfortunately. And the last is we were talking before, incomplete penetrance. So why this subject, like in this family, who carry 3 mutations in 3 different genes, develop the disease, and why the other patients, the other family members who carry at least 2 mutations never develop the disease? Unfortunately, the genetic test so far can tell you that. Last thing, I would like, first of all, thanks all the people of the mall. You probably understand from my funny accent that I'm not American. So, and I would like to say how beautiful and amazing is working with these great people in this particular place. And again, thank you so much for listening. And if you have any questions, please.